we're trying to find out the frequency response of various active microstrip components like a pin diode fixed attenuator, a low noise preamplifier, a voltage controlled oscillator, a Schottky diode detector, a pin diode switch, a circulator, a pin diode variable attenuator, a double balanced mixer, an MMIC amplifier. So we'll try to find out the frequency response of all of these components using the microstrip training system provided. We want to find out the frequency response from 2 to 4 GHz. We have set the instrument to 0 dB cal position by applying a through SMA connector, and we'll try to find out the frequency response of various components. Now we begin by finding out the circulator response. Circulator has got a clockwise power distribution, so a power being applied on port number 2 is available at port number 3, power applied at port number 3 is available at port number 1, but the power applied at port number 3 is not available at port number 2. So the power only rotates in this direction. So we'll try to apply the power at port number 2, and we'll try to find out the power available at port number 3. The unused port is terminated with a 50 ohms load provided. So now we can see that this is the frequency response. We press the auto Y button. So we can see that the insertion loss of the circulator from port 1 to 3 is of the order of about 3 dB. So we can find out the isolation of the circulator by trying to find out the port response between different ports. So we can see now different port parameters can be likewise be measured. In this case, now we see that the isolation is of the order of 16 dB at the center frequency of 3 GHz. So we have got an analogy between different waveguide components, and all the components which are available at the waveguide domain are also available in the microstrip domain at 3 GHz. Now we try to find out the frequency response of an MMIC amplifier. We did the cal at 0 dB, but the power gain of the amplifier is roughly about 20 dB. So we need to reduce the power level by applying a less power. So we can see that we have reduced the power level by about 30 dB right now, and we have again done the cal. Now we apply the power at the MMIC amplifier. Now we power on this MIC amplifier by applying a DC voltage through a variable and a fixed power supply here. So we see we have connected a power supply. The moment we have connected the power supply, we can see that the curve has shifted from 0 dB from where we called to roughly about 20 dB. So we can see that the amplifier has provided us with a 20 dB of power gain at the frequency from 2 to 4 GHz. Now in the similar fashion, we'll try to find out the power gain or the 1 dB compression points. All these measurements can easily be performed with the system that we have here. There is no other instrument which is required to perform the experiments in the following lab. So we can see the frequency response of the LNA. Now you can see that the LNA has a frequency response of roughly about 10 dB gain at 3 GHz, and the gain is about 14 dB at 2 GHz, and the gain is about 8 dB at 4 GHz. So this is the gain of S12 of the low noise amplifier. In the similar fashion, we can find out the characteristics of other devices. Say we again do the cal with through cal provided, we apply full amount of power. We take the cal data. Now the cal is being applied, it is normalized to 0 dB again, and we want to find out the insertion loss characteristic of the pin diode switch. The pin diode switch is being connected, and we can see the power has not been applied, so this is S1 to 2 is the isolation characteristic of the pin diode switch. So the switch is roughly about -22 dBs at 3 GHz. So this is the isolation characteristic of the pin diode switch. The moment we apply the power, this is the on condition of the switch, and we see that the insertion loss is something of the order of 2 dB for the pin diode switch.